Hello again. So we are going to continue working on the partial differential equations, and now I want to go to the next topic, which is a very important topic for solving these PDEs, and that is the characteristics and characteristic curves in these PDEs. So this is going to give you a very good insight into actually how these PDEs, what are the solutions of these PDEs, especially these canonical linear second order PDEs that we discussed. And also, in general, it's going to give you a method in which you can use for more complicated and complex PDEs, and it's very useful method because it is very insightful, and you can easily use this to solve some simple PDEs. Okay, and in order to do that, we want to find the characteristics or characteristic curves or characteristics in any PDEs, and in order for you to understand it, I'm gonna start with a simple example for a advective advection equation, and after that we're gonna generalize these characteristic curves method for more cases, and after that we are gonna see what were the types that we were discussing and how you can get those types from this characteristic equation, like elliptic or hyperbolic or parabolic types that we were discussing in the previous session. Okay, so consider a simple advection equation with the form du over dt partial u over partial t plus v partial u partial x equals to 0. And this is equation 1. Okay. So now I want to write an expression for u. U can be a function of x and t. Okay, it's a general function. So we can write for u, which is a function of x and t, it can be a function of x and t. We can write it as du, total u difference. So because this is a function of both x and t, so in order to find the difference in u, what we can do is we can separate it into the derivative in x and t direction, right? So I'm gonna do this. So the derivative of u partial u over partial x times dx plus partial u over partial t times dt, right? So what I've done is that I have now written du or u as a function of x and t, okay? So for you to understand it better, and now let's show it this way. If we plot, let me plot it here. This is x and this is t. So if we plot, say, these x and t, so this is gonna be dx. Say we have a difference in x, and here we have a difference in t. And This is like the board. This is like the vector, and this is the difference here. And we assume now I want to assume that u is known in this vector. Okay, in this vector that I plotted, I want to assume that u is known to proceed with this. So assume that u is known along the line with slope dx dt. Okay, so assume that u is known along this line, and with this I want to write this equation that we have written before, divided by t, and write it as this equation. With this condition that we have, we can write it as this du over dx dt plus du over dt, and these cancels out. And in other words, I can just rearrange the terms and get du over dt partial u over partial t equals to total d or du over dt minus partial u partial x dx over dt. And I name this equation equation 2. Okay, so now if we substitute this u here into this equation, we are gonna get a new set of equation. And so that is what I'm gonna do. So substitute two into one, and what I'm gonna get is this equation. Du, instead of partial u over partial t, I'm gonna write du dt minus partial u partial x dx dt plus v partial u partial x equals to 0. Okay, so this is the equation I'm gonna get, and I'm gonna just rearrange the terms again and get an expression for du over dt equals to, I'm gonna factor du partial u partial x, so I'm gonna get dx dt minus v times partial u partial x. Okay, so this I got from the previous equation, and now I wanna ask some question. I wanna know that if du over dt is known or given, can we solve for du over dx and find du over dx? Say we know some values of du over dt. Can we solve for du over dx? So the answer to this question is yes, and we are gonna investigate this question. So the question is, given du over dt, a value for du over dt, can we solve for partial u partial x? And the answer is yes. except when v equals to dx over dt, right? Then because it becomes 0, and once it becomes 0, then we cannot solve that equation. So let's say if du over dt, I want to say if when du over dt becomes 0. So now I want to see what happens when dx over dt equals to v. Okay, so when dx over dt equals to v, du over dt becomes 0. From this equation, you can see it, right? From this equation here. So when dx over dt is v, du over dt becomes 0, and this means u is gonna be constant, right? U is not gonna vary. It's a total derivative of u with respect to time, and so u is not gonna vary. U is gonna be constant. Okay, so let's see what does this mean in the if we plot it. Okay, let's see what happens if we plot it. So you are gonna get something like this. If we are in the xt space, so here is x and here is t. So what we are going to get is this. So what we are going to get is lines parallel with each other and with slope of 1 over v here in this xt space. So the slope here is gonna be 1 and v. Okay, so for these lines, let's see what do these lines mean and what are these lines. Okay, so these lines actually are just dx over dt equals to v, right? So these are the lines where dx over dt, let me write it with another color. So here in these lines, dx over dt becomes to v, right? So I just plotted these lines, and let's see what do these mean and what do they do. Okay, so along these lines where dx over dt equals to v, we found here that du over dt should be 0 or u should be constant. So along these lines, u should be constant. So I'm gonna write it here. So for example here, u is gonna be constant. So along this line, whatever the value of u is gonna stay constant. Okay, so say here we can say we are at x1, just a value. Okay, and I'm gonna say the value of u is gonna be ux1, and because t is 0, I'm gonna just write it ux1 and 0. Okay, so as you move along this line, u is gonna stay constant here, it's not gonna vary. So u even here is gonna be x1 and 0. Say another point, say here say we have t1. just a name. And the value of u, say, is, because we are at x equals to 0, so it's going to be u0 and t1. So the value of u is going to stay constant along this line here, and is going to be u0 and t1. Okay, and the same for all other points. You can just find it like this. And just to remind you, here this part is initial condition. So this is the initial condition of our problem, right? Because t is 0 here, and let me choose another color. Here, this is the boundary condition, what we call boundary condition, right? Because your x is at 0, right? So this is the boundary of our solution. So what actually does, first I want to say, what are these lines? So these lines are actually what we call characteristic curves. So these lines are where our solution just propagates along these lines. Any solution that we have in our PDE propagates along these lines. And for this simple advection, advective equation or advective transport equation, the characteristic line is, characteristic curve is very simple. It's just dx over dt equals to v, okay? And our PDE solution, the solution of u, is gonna propagate along this line. It's gonna stay constant and just propagate along that line. So the solution of this equation, just propagates initial conditions. So this is initial condition. You see, any point that you say here, like here or here, whatever, this is, if you continue this line, it's gonna just propagate either the initial condition here or the boundary condition here, right? So if you know the initial condition, this green line that I plotted here, and this orange line, the boundary condition here, then you have the full solution of this problem. So the solution of this equation propagates initial condition and boundary condition, BC information, along characteristic curves, and u, x and t at any point in space and time, x and t, can be found using the initial condition, or u at any x 0, and boundary condition u at x equals to 0 and t anytime. So this is initial condition and this is boundary condition. Okay. So this was the overview of characteristic, simple examples. So you learn what is characteristic curves and how do they work in PDEs. And just to give you a practice problem so you can work on this. So a practice problem, just you can work it at your home to get more familiar with this. Plot ux and 4, which is just u at any x and t equals to 4. Like 4 can have a unit, for example 4 seconds, given this equation. So du over d partial u partial t plus v partial u partial x equals to 0 for x greater than 0 and t greater than 0. Okay, and the partial u partial t, this is just the transport advective equation, and the initial condition for this problem is ux 0 equals to 10 minus x when x is between 0 and 10, and 0 when x is greater than or equal to 10. And the boundary condition is u at 0 and t is 8 minus t when t is between 0 and 8, and 10 when t is greater than 8. Okay, so it's a very simple problem. This is the initial condition and this is the boundary condition, and you just put it here and then just propagate it in space. And then I just want you to plot just one line of it, that is ux and t equals to 4, and that means somewhere around here, right? So you have to just plot it around here. So you have to find what is the characteristic here. And v, I can give you a number for v. So let's say v is 5. Okay. And using this, you have to find two regions and then just propagate the solution here to here and solution here to here. So this was just to give you what does characteristic how does characteristic curve look like, and this is for the whole. This is just a simple example of that, and in the next session, what we are going to do, we are going to generalize this. So for a general function, how what we should do to find for a second order linear PDE, what we should do to find these characteristic curves, and especially for those canonical problems that we talked about, we are going to find these characteristic curves, and based on that we are going to classify those equations, those partial differential equations, to those three types that we talked about. Okay, everyone, thank you very much, and have a good weekend.